right. Thank you, Nutti, for the kind introduction. And as Nutti mentioned, my specialty within mathematics is matrix theory. So one good thing about matrices is that they interact not only with different branches of mathematics, but also other disciplines in science and engineering. So in this slide, I've collected a few examples of my favorite applications. Matrices are important for the theory of computation. They are useful for problems in pure algebra. They are tools that can be used for designing practical computational algorithms. And they're also linked to this network analysis. And as Nutti anticipated, I'm going to stay in this top right corner of this scheme today. So I'm going to tell you a story about network analysis. All these applications are actually interconnected, so they're not completely separated. The topic in particular that I'd like to discuss today is something that we call centrality measures. So mathematically, they are non-negative functions that are defined on the nodes of a graph. But more often than not, these graphs come from practical applications. And you have a phenomenon where that can be modeled at least with some actors, so some things or somebody that do something, and they represent the nodes, the vertices of the graph. And the edges, so the connections between the nodes, are some interactions between these actors. And well, there's many questions that one could ask at this point, but the one that I'm going to talk about is the following. How can we rank the actors? Which are the most important ones in this phenomenon? And what does it mean in practice? Of course, depends on the application one is coming from. There's really many examples that one could make, but for instance, just a few here. In social sciences, the graph could come from a social network, perhaps. I don't know, Facebook or X, one of the big ones. And you may want to know which are the influencers, the people that the users of that social network listen to. If it's biology, perhaps there's a disease spreading. You want to know the super spreaders, those people you should stop to stop the pandemic. If it's finance, then maybe the nodes are stocks, the links are correlations, and you'd like to know where to put your money. Nowhere at the moment because the stock exchange is plummeting, but in general, this makes sense. Sometimes these graphs are very large. If you think, I've mentioned Facebook, say, or X, and then there's billions of users. So it's not really just 6 nodes. There could be 6 billions. So you want a method that not only allows you to compute things, but it's also fast, because you may want to compute these things frequently and in a very short time. So that's an aspect you keep in mind. And one way to rank these nodes is based on a concept called walks. And by the way, I'm not doing this by myself. So here's, as a thank you slide, is my collaborators. Some of them are local at Aalto, others are elsewhere. But before I tell you a bit more about what a walk is and so on, here's a sort of motivational slide. So here's a graph, slightly larger. And I want to ask the audience a question. Which node would you say is the most important here? And somebody should say something, otherwise they're going to need to edit the video. 1. Yeah, that's what most people say. So intuitively, if a human at least looks at this graph, well, 1, if you remove it, for example, everything gets disconnected. And also, I introduce a bit of bias. I just drew it in the center of the picture, of course. But I'll come back to this picture later on. Let me go back to the issue. So we want to define this function of each node that assigns a value of each node, and then I look at the value and I want to rank them depending on this value of the function. And somehow this should tell me which nodes are the most important. That's the goal. And I want to do it in a mathematical way. So this question is, of course, posed in a sort of vague manner. One wants to mathematize it. One good way, for reason that I explain in a second, is to base the function on a concept of a walk. So what's a walk? Well, it's what you may think it is. Like if I go back to this picture, you walk from a node to another one if there is an edge that lets you do that. So for example, here I could go from node 1, say, to node 20. There's a connection. then to 26, then I'm forced to go back to 20, there's no other thing to do, then you could go to 28. So that would be a walk. But you cannot go, for example, from 1 to 16 because there is no direct connection. So really what you would think a walk is. And it turns out that if you use this walk to define a centrality measure in a way that I will explain soon, these are sort of, let's say that it's a friendly approach, friendly for people who like matrices. And so you can translate, if you want, your graph to a matrix, and then you can do easy or relatively easy computation on your matrix. And this tells you, for example, how many walks you have from a certain node to another one. And well, this is well known. In fact, one of the first centrality measures that were defined in the history of this topic is called cut centrality because it was discovered by one Katz, who was not a mathematician, by the way. He was working in social sciences and psychology. And well, the idea is the following. If you define this matrix, it's called the adjacency matrix of the graph, you raise it to the kth power, so something that my students know how to do. And it turns out that the ij element of the kth power of this matrix counts the number of walks of length k from node I to node j. And Katz's idea was, okay, let's start from node I. Let's try to count all the walks that I can make from that node. And this would give me the importance of that node. There's a problem. If you do this, usually there's infinitely many walks. So mathematically, we say this sum doesn't converge. But you can do a little trick. So you say, OK, longer walks are a bit less important to explore the graph. So let's put a weight on the walk that depends on the length. And in this case, it's something that decreases exponentially. So t is a parameter between 0 and 1. You give a weight t to the k to a walk of length k, and then you do this weighted sum. And this, at least for some values of t, does converge, and it gives you a number for each node. That tells you arguably how important a node is. The concept makes sense. It's relatively simple. And moreover, it turns out, you don't have to worry about the details. This is a math talk, so there are some formulae, but no need to worry too much. The point here is that you can do this very efficiently. Even if you have a very large graph, you can solve this problem and compute this cut centrality very efficiently. But this is 1950s mathematics, so it's not what we did. What we did is to refine a little bit the counting of walks. So let me give you another definition. A walk is backtracking if it backtracks. So if at some point I go from node I to node j, and then immediately back to node I, this is a backtracking walk. If I never do that, it's non-backtracking. And we wanted to do something similar to cuts 60 years ago, but only keeping non-backtracking walks. And well, the mathematics becomes more difficult. Here are some more formulae. They look probably a bit more complicated than before. But, well, we are mathematicians. We have more fun if the math is more difficult. So we wanted to figure out how to do this. Why? Why did we want to do that? Well, there's certain contexts where this makes sense. One is if you want to model the spreading of information, for instance. So useful information typically doesn't backtrack. If you liked my talk, perhaps you will tell someone else, so there's this guy, mathematics, does this and this thing, but you won't tell it back to me, because you know that I know. Irrelevant information could come back. If you tell me your research sucks, maybe I don't know, your research sucks. But so this could act, removing backtracking could act as a sort of spam feed. Or very popular thing recently, disease spreading models. So if I infect you with a virus, you could assume that you cannot infect me back because it's more or less the same virus, so I'm immune, say. But the virus could come back after a longer cycle because the more people it visits, the more likely it is to mutate. And, well, we've all read lots of things about this in recent years. So anyway, there are some contexts where actually it makes sense to remove backtracking walks. So we had the motivation coming from the application. We did the math. And here I am back to the galaxy graph. It's called galaxy graph because it's made of 3 stars, if you want. So this piece is a star. There's a center of the star and some rays. And they're connected through a center of the galaxy. And we said we'd like node 1 to be the most important somehow. In general, you could generalize this graph. You could take m stars with n nodes each. And then the answer depends on these 2 parameters, m and n. And, well, cut centrality converges for, there's a limit. So the parameter t cannot be larger than this value, whereas the new centrality always converges for any value of t. So apparently phase advantage, but according to how you choose M and N, well, there could be a sort of phase transition. So for small values of t, cut centrality and also our centrality can fail to rank node number 1 as the highest, as the most important. This is because, well, it's well understood in this business, small values of t is a sort of naive thing that nobody really wants to do. But the point is that cuts cannot reach sometimes this phase transition. So it always ranks some other nodes better than 1. Whereas our method for sufficiently large t can. And this is sort of satisfactory. But of course, this was a sort of toy model. We built this graph. And then it makes sense to try the same method to apply to actual graphs coming from actual applications. So we have done this. Before I show you a couple of results, I should probably say that the world can be more complicated than what I showed you so far, even if you do some modeling and some simplification. So one thing that often happens is that the connection between the nodes of a graph could have a direction. Facebook is not directed, right? If you're friends with somebody on Facebook, somebody must be friends with you. But X, the other big one, can have a direction. You could follow somebody, and not necessarily that somebody must follow you. So there could be a direction on the edges. There could be weights. Another example I made was from finance, so correlation between stocks. And the correlation is actually, even if we take absolute value, it's any number between 0 and 1. It's not a binary thing. So you could have weights on the edges, or not just existing or not. Sometimes the graphs come from things that you measure with the frequency, say every year or every day or every minute. So you really have a sequence of graphs, or if you want a graph that changes with time. And you may want to deal with all these things. And, well, short summary, we can deal with all these things. They must become even more complicated, but we were able to derive formulae and recipes. We can also change the weight. Instead of just doing t to the k, we can do fancier thing. We can, if wanted, also exclude further types of cycling. Say, backtracking is something that is a cycle of length 2 if you want. You go back after 2 steps. Maybe you don't want to even go back after 3 steps or 57 or whatever. We can exclude any length of the cycles with a price, but never mind. And OK, here's one table. You don't have to worry about all these figures, but somehow the second fraction that you see in this row is more or less the fraction of computational time that it took to us with respect to the classical approach cuts. So even if the math is more complicated, actually we are faster because tricks and well, not tricks, but mathematical properties of the new measure. So this was at the time X was still called Twitter, and Twitter actually gave us data about UK users, and they wanted to know who are the most important users, and I think they used these to make money. This is another test that we tried. So this is a graph coming from biology, and it's a common way to test your method because sometimes you don't know what the truth is, right? You don't know who is the most important node in the graph. But in this case, you do, because this is a graph coming from biology, something happening in a yeast cell. And each node is a protein. And biologists know which nodes are important in the sense that if you turn them off, the cell dies. So you can sort of test, is your method able to detect the important ones? And we did particularly well with respect to the previous measure. So, okay, even in this case, it seemed that removing my tracking was useful. Okay, and I don't know if you can see very well here, we had some problems with the projector previously, but this is a graph. It's a huge graph. It's coming from the email network from the US government email during the COVID crisis. And here you see the big dots are the important nodes, and the small dots that you maybe don't see very well are the least important nodes. But we tested this in one of our papers, and there was a sort of a surprise. So I'm sure you've all read the name of Anthony Fauci. It was this important US doctor who was the head of the project. But using this non-backtracking centrality, it turns out that, at least for large values of the parameter t, he was not the most important person in this email communication. It was someone else called Jeremy Farrar that I had not heard from newspapers. I had to figure out who he is. And he's a British medical doctor who acted as a consultant. And maybe he was the mind really behind the scenes. Or at least this is what the analysis of the network told us. OK, this was my last slide. So thank you very much for your attention.